Okay, now let's suppose we have some raw data. So section 3.9 in your book deals with that. How are we going to put that data in your calculator, have it plot, find the linear that fits the best, and then how are we going to interpret what we're using, our model, and then how are we going to judge the strength of our model? So let's look at this personal information. According to a poll, people are more concerned about privacy issues than about healthcare, education, crime, or taxes. Now, I need you to know that we really do care about the source of the poll, okay? Some are more reputable than others, and as you mature and continue your learning and thinking and judgments, you will find that some are bad and just not well done, and some are very careful about how they draw conclusions. So we do care about the source. The percentages of Americans of various age groups who consider their home address to be personal information are listed in this table. So the question is, do you consider your home address to be personal, private information? Okay, you probably have an opinion that you're thinking about. So they sent out a survey in different age groups, and the age that they're using to represent this data group is the middle age for these groupings. And then they computed the percent within that age group who said, my home address, well, that's my business and none of your business. Okay? Because it wasn't too long ago that we had huge fat phone books full of everybody's name, their home address, and their phone number. So here's that information, and the first thing we're asked to do is construct a scatter plot using the calculator. Okay, so I'm going to slide my data to the side and bring in good old calculator. Okay, in order to put the lists in, so just to remind you, I'm going to go Stat, and then I'm going to hit, I think I should turn off the light for this. There we go. Is that better? There, that's better. And then I'm going to hit Enter, and I'm going to put in the age into L1. So 21, 29 and a half, 39 and a half, 49 and a half, or around 59 and a half, and are you around the age of 75? And 84% of younger people with home address said it was personal. 80% of around 30-year-olds, 74% of around 40-year-olds, 74% again around 50-year-olds, 67% of 60-year-olds about, and 60% of people around the age of 70. Well, 75. Older. The older group. So let me zoom out. Well, actually, we need to make a scatter plot, don't we? So let's remember how to do that. Okay. Do you see stat plot here? So second, y equals, brings us to this screen. I'm going to hit Enter. I'm going to turn it on. And by the way, this is exactly how you would turn it off when you're not trying to plot these points, and that's a scatter plot. My x's, or my explanatory variable, that is L1. That's the age. And the y list, or my response variables, is the percent of them who said it was personal. Now I'm going to go to Zoom. So down here, there's a Zoom button, and I'm going to go to Zoom Statistics and hit Enter. And here's the image we get. All right, let's put that on the page. Construct a scatter plot of this data using your calculator. Okay, So along our vertical axis is going to be our response variable, and that's the percent of Americans who consider their home address to be personal information. Now, I'm going to have to paraphrase that. So, percent who think it's personal. Okay, now I left off a lot of information there because it's actually, it says Americans. It said Americans in the source, but I prefer to say it looks like really these are adults in the United States, right? Adults within the United States who consider their home address to be personal information. That's really what our vertical axis is. And our horizontal is our independent variable or our explanatory variable. And here we are considering that to be age. We're thinking that age explains whether you responded it being personal or not personal information. So, and by it we mean the address. Let's make a quick plot of this based on the screen we had. So, something roughly there. Got it. Sure. There you are. And then there you are. And then there you are. Something roughly like that. Remember your labels. Oops. How close is this data to looking like a line? I feel like it's pretty close to being linear. I mean, it's pretty close. Pretty close to being linear. Is it increasing or decreasing? Looks like it's going down. It's decreasing. So as age increases, so the older you get, the less you feel like it's personal. Like, who cares? So it is decreasing. Okay. Find an equation of a linear model to describe the data. Use your calculator. Write down what each variable represents. Okay, here we go. Back to the calculator. Whoop. All right, so we're going to need to go to Stat. And now we go to Calculate. And instead of doing one variable statistics, which we did to find the mean, the median, the standard deviation, we are going to go to number 4, which says linear regression in linreg form. Okay, I don't want L4. So I'm going to put second L1, enter. Okay, that put the ages in my X list or my explanatory list. And I do want L2, which was the percentage, as my response variable. Okay, and calculate. Now, the first time you do this, you might not get this R squared and R, which is called the correlation coefficient. And so you will need to turn on your diagnostic. And on the calculator, that literally says diagnostics on. So there should be a video about how to do that, but just FYI. It looks like the A, which is our slope here, is negative 0.431-ish. So we're going to have to round it, obviously. Let's go to 3 decimals. Okay, so now that I have this on my calculator, I can write this down. So I'm going to write down Y, and we're rounding things, so I'm going to go ahead and use this estimation. Negative 0.431x plus, says 92.854. Okay, so I kind of like this and I kind of don't. So what I mean by that is it's so abstract. I don't know what y represents and I don't know what x represents. So I'm actually going to go ahead and change this just a little bit to being, okay, what was y? Our responding was the percentage. So I'm going to use p for percent. It's still an approximation. And negative 0.431. And what was the explanatory variable? Age. Age. So I'm going to go A. A for age. Plus 92.854. And I also want to take this one step further and mention that we usually write this as P is approximately 92.854 minus 0.431A. That shows us it's initially, if A is 0, this initial value is 92.85%, but it's decreasing for each A and age. So the more age you have, then the more decreasing of this percentage happens. Okay, write down our value. If your calculator, okay, so watch the video to turn this on if your calculator isn't showing it, but mine certainly is. So I'm rounding it, is negative 0.987 is what my calculator said. And that I'm going to turn into a quick percentage, which is negative 98.7%. Okay. I'm going to be using this to judge how good. So when we said, is this linear? Pretty close. And then I look at this and I'm like, oh, you know what? It gets an A. It gets an A in being linear, and it's decreasing. So that correlation coefficient, that's going to be one of our measurements for how good is this model, or how close is this model to being linear. Well, it's pretty good. It's a pretty nice percentage. A lot of people would love to have that in their math class. Anyway, what is the slope of the linear model? Ooh, well, the slope, remember, is this constant change here. So the slope, which is constant change, we rounded it to about negative 0.431. Interpret the meaning in this situation. Okay, so the percent, oopsie, of U.S. people, adults really, they didn't ask anyone below 18, percent of U.S. people who think their address is personal decreases by 0.431 for each additional year they age. For each year older they get. How about that? I'll just leave it like that. Yeah? Okay. Next problem. Number 6. Rewrite the linear model using function notation. Okay, it definitely passes the vertical line test. For every input, there is exactly one output. So it's a function. So let's rewrite this as, I don't know, I'm going to go percent, depending on age, is about equal to, still would love, maybe I just prefer, because once we've rounded, 92 point, and we are in a model, so perfection is, I mean, come on. There's always going to be some flaws in your data. So 92.854 minus 0.431. Got it. And let's see. Use your equation and not the data in the table to find, oh, you know what? This says F. I'm going to change that to a P because that's what I decided to use. P of 49.5. Interpret the meaning in your answer. Okay. Can do. Whatever you want. So this is then what, the age? P of 49.5 means replace the age for a 49.5-year-old. So 92.854 minus 0.431 times 49.5. That is pure calculator business if I ever saw it. So I am putting that into my calculator and I get 71 point, I'm rounding it, 71.5 about. Okay, so about 71.5% of 49.5-year-olds think it's personal. Okay, and so just to, yeah, I think number 8 really gets to my curiosity. Just to see how far off is our model, right? Because the calculator picked this equation for this data set because we knew it couldn't be perfect, but we were looking for the best fit, like the least amount of error, total error. How far off was the model? So the model means, by the way, best fit estimated line equation, okay? That's what model means. How far off was the model to the actual data collected for that group? Okay, this is called residual. So let's see here. We're going to go back to our data. And this 49.5 was actually 74%. Okay, so let's see. How far off? Well, I'm going to go change, which is the difference is it was really 74%. You know, I'm going to use our formula that we remember about change, and that was new amount minus original amount. Okay, well, the new amount is the model amount, so 71.5 minus the original that we knew was actually 74. How much difference is that? 71.5 minus 74, negative 2.5. Okay, so here's the residual. This is how far off the model was from the real percentage that happened for that age group. And what is that? That's so it was, the model was 2.5% below what actually happened. So I need you to know that models are really great at predicting, but they're never completely accurate. I mean, if they're accurate, that's really, I mean, the likelihood of it being perfectly accurate is really slim. The likelihood that your data is perfectly linear is also very slim. But nonetheless, here's how we found how much it was off. It was an underestimate. Okay, there's this group of instructions here to talk you through how to use your calculator, right? And I just wanted to put it here just in case you needed a reference. or wanted one. I think your book tells you how to do it too, and there's videos out there, right? How to use a TI-83 or TI-84 in order to do it, whatever. But anyway, you can even make those on Desmos. But okay, so an association. Let's talk about all of these different words. Association, so are two things associated? Are they correlated? And do they cause? Does one cause the other to happen? These are all legitimate questions that we apply in general to our life. An association is when one variable is related or associated. Okay. I'll even put that, even though I'm not a big fan of using the word itself inside its definition. Associated, related to another variable. Somehow. And I think that this makes a lot of sense in terms of the word association. I don't know why I put a period there. When I think about being associated with another person, then somehow, I mean, we're not directly related to each other, but somehow there's a relationship through something, right? So here it is in terms of mathematics. So one variable is related to another somehow. The two quantities have some kind of relationship. A correlation, so correlation, is a strong linear relationship. So if two things are correlated, they have a strong linear relationship. Okay? Maybe I'll put strong linear relationship between two variables. Okay, so if there's a strong linear relationship, then we actually use the term, they're correlated to each other. And then causation, I'm very popular. Just got a text message. Causation is when changing one variable causes a change in the other. So causation. When change in one variable I did it again. I used cause in the definition of causation. When change in one variable cause or makes the other variable change too. Okay, so we use this word a lot. And associated. When one variable is associated with another one, somehow there's a relationship between these two variables or ideas. And then a correlation is a strong linear relationship, so we use that term a lot too. They're definitely correlated to each other. And then causation, we are shy to use this word, causation. And maybe you haven't even heard that word causation. I'm sure you've heard the word cause. But causation is when one variable actually makes the other one or causes it to change. And that means you have to have way more than just data to support your claim. So causing something to happen has a deeper meaning or understanding than just they are related and there's a linear relationship between the two. Okay? Now, the linear correlation coefficient, that's R, and that measures the strength of the linear relationship. So measures the strength of the linear relationship between variables. So when I said, or when I asked the question, how close is this data to looking linear? And I'm like, yeah, it's pretty close. Well, how close? I mean, give me like a measurement. Like, is it super close? Not very close? And in the middle of that last example, we found that it was what, like 97.5%. And that's pretty good. Pretty strong relationship. Okay, let's do a few remarks about this. 1, best fit lines will always have some amount of error unless the data forms a perfect line. So, which is very rare. Data is, there's always flaws in data. So, best fit lines will always have some amount of error. Unless the data is perfectly linear. Okay, and then even then I would be like, is their data right? Okay. Another thing that's remarkable is that means that the closer R is to 100%, the closer the data is to being aligned. So, the closer R is to being 1, which by the way, 100% or -1, because that would also be 100%, just decreasing. So the closer R is to being 1, the closer the data is to being linear. Okay. Third remark about this whole process is if the line is going down, R is negative. If it's decreasing, it's negative. Okay, so being positive or negative just means it's going down or it's going up, the relationship. And my last remark, sure I'm going to say a bunch of stuff though, is that correlation does not always mean causation. Okay, and I'm going to show a quick example of this before ending this video. Example 2 says correlation is not causation. They are not the same. That's why we have two different words for them. Here is a pretty linear, look at that, 97%. Wait, no, that's R squared. What is the square root of that? Hold on, 0.97, square root of that. 90, it would be R, so I'm actually going to write this in here. If we take the square root of that, R is approximately, what, 0.985. Okay, that's pretty strong. I mean, that's pretty linear data. And let's see what this data is talking about. Okay, the total U.S. highway fatality rate, that they're saying that depends on knowing the number of fresh lemons imported to the United States from Mexico. Huh, right. So the more lemons, the more highway fatalities we have. No. So these are definitely correlated. Okay, so when we go back to this list of words, there is a strong, so they're associated maybe. They're definitely correlated. They have a strong linear relationship between the two. But when you change the number of lemons, do you change the number of fatalities? And when you change the number of fatalities, will that change the number of lemons? No, come on, that would take a lot more of evidence to support that claim. Okay, so make sure you're not mixing up these two words. Okay, in the next examples, we will take a look at this correlation coefficient, and we'll look at a massive data set that I recommend you put into your calculator before watching the next video.